students, welcome back. In this video, I'm going to solve a tricky question based on the acidic strengths of the carboxylic acid. So let's get started. Before we start solving this question, I want to explain to you why carboxylic acids are acidic and what are the different factors which will influence the acidic strength of the carboxylic acids. Let's understand why carboxylic acids are acidic in nature. Let's take any carboxylic acid, so RCOH. When it is taken in water, it dissociates, right? This dissociates and donates the proton, and then it forms the conjugate base. Since it donates the proton, we call this as an acid. So it's a carboxylic acid in this case. Now, the formed conjugate base is stabilized by resonance. So this is the driving force for the carboxylic acid to be acidic in nature. Now, what are the different factors which will influence the carboxylic acid's acidic strength? The first factor is the presence of different groups like electron withdrawing groups. Electron withdrawing groups like aldehyde, ketone, nitro, cyano, all these groups will increase the acidic strength of the carboxylic acids, whereas electron donating groups like alkyl groups like methyl, ethyl, etc. will decrease the acidic strength of the carboxylic acid. This is common for all the carboxylic acids. Then what about the aromatic carboxylic acids? So for benzoic acid, which is aromatic in nature, we have two extra factors which will influence the acidic strength. What are those? The first one is, it's called as ortho effect. This is very important. So let's discuss that in detail. And the second reason is hydrogen bonding. What exactly are these? Let's take examples and discuss. So, what is ortho effect? The ortho-substituted benzoic acids are always stronger than the benzoic acid itself or any other meta or para-substituted benzoic acid. Regardless whether the substituent is electron withdrawing or electron donating, it's always will be more acidic than the corresponding meta or para substituent groups. So it could be anything, either methyl, ethyl, or nitro, chloro. It doesn't matter. Okay, X could be any group, but the ortho will be always more acidic than the meta or para, or even more than the simple benzoic acid also. Why so? Because of the steric hindrance at the ortho position. What do you mean by that? Whenever you have a carboxylic acid like this, right? So if there is any group, okay, so in this case I'm taking R, right? What happens, because it is taking the ortho position, it needs more space here. Therefore what it does is it will literally kick out this hydrogen as a proton. So it's making this hydrogen to leave the molecule as proton easily. So that's the reason any ortho substituted benzoic acid will be always more acidic in nature. But in the given question, all of them are ortho-substituted. In that case, how we are going to decide what will be the acidic strength of the given molecules? For that, let's understand hydrogen bonding in benzoic acid molecules. By now, you might already know what is hydrogen bonding. If you don't know also, it's okay. I'm going to explain this quickly here. Whenever hydrogen is attached to electronegative element like fluorine, oxygen, nitrogen, it will have partial positive charge due to electronegativity of these elements. So then what it does is it will start interacting with the electron-rich electronegative elements like fluorine, oxygen, nitrogen from the neighboring molecule. So because it is electron deficient, so it's kind of interacting here with the electronegative element like fluorine, oxygen, and nitrogen. In this case, it's going to be oxygen. So what is this interaction called as? This is called as hydrogen bonding. How this hydrogen bonding is helping us to understand the acidic strength of the acid. So for that, let's take the example of salicylic acid. Salicylic acid is ortho-hydroxy benzoic acid. So here this bond is weak. Why so? Because of the ortho effect, the hydrogen will be leaving the molecule as a proton, and then it's going to form the conjugate base. So here the conjugate base is carboxylate, right? So this is the carboxylate. Now, this carboxylate is additionally stabilized by the hydrogen present here due to the hydrogen bonding. So this is a intramolecular hydrogen bonding. Why intramolecular? Because it is within the molecule. That is one reason. The second reason is that it's forming a kind of six-membered cyclic structure. Look at this: 1, 2, 3, 4, 5, 6. So this will give additional, that means extra stability to the molecule. So first of all, there is a ortho effect, and then there is a hydrogen bonding which is intramolecular, and it is imparting extra stability to the molecule by forming a six-membered transition state structure. Therefore, the hydrogen bonding is imparting extra stability to the carboxylate ion, which in turn makes the corresponding acid as more acidic in nature. Now, let's apply this concept for the given molecules and find out the correct order of their acidic strength and choose the correct statements also. Now, let's analyze the molecules. So, this is salicylic acid, and this is called as resosilic acid, right? And this is orthomethoxybenzoic acid, and this is dimethoxybenzoic acid. The molecule 1 and 2 will exhibit ortho effect as well as intramolecular hydrogen bonding. Therefore, 1 and 2 must be more acidic as compared to 3 and 4, because here, although there is a methoxy, look at this. Once it forms a carboxylate ion, we have OCH3. The hydrogens are there, but they will not exhibit hydrogen bonding because hydrogen is attached to carbon, not oxygen, not nitrogen, not fluorine. Hence, we cannot show there is a hydrogen bonding here. So there is no intramolecular hydrogen bonding, means obviously 3 and 4 will be less acidic as compared to 1 and 2. Between 1 and 2, obviously 2 will be more acidic in nature, because more the hydroxyl group, more is the stability of the carboxylate ion. Hence, so here 2 will be more acidic than 1. Between 3 and 4, how do you know which will be more acidic in nature? So there are two groups at the ortho position. So more the groups, more will be the acidic strength. Therefore, what happens? 4 will be more acidic than 3. So this is the correct order of acidic strength. Let's look for the statements. The order of acidity given is 2, 4, 1, 3. So what do we have? 2, 1, 4, 3. Therefore, this is a wrong statement. Now, let's check for the second statement. The magnitude of pKa difference between 1 and 2 is more than that of between 3 and 4. See, you can't remember the pKa values for all the molecules. I have already told you. See, these are way more acidic, right? And their difference will also be more. Therefore, this is a correct statement. Now, let's check for the third statement. Intramolecular hydrogen bonding is more in 4 than in 3. Is that true? No, because there is no hydrogen bonding here. So this is a wrong statement. So let's check for the last. Intramolecular hydrogen bonding makes compound second the most acidic among all. So this is correct statement. This is what we have seen, the intramolecular hydrogen bonding and how it makes the resosilic acid the most acidic in nature. Here I'm going to give you the standard pKa value for all these compounds, because you can compare their pKa values and also take the difference of the pKa values in order to give the justification for the given statement. So here the first one is 2.97 and then 1.30. Third one is 4.09 and the last one is 3.39. So remember, lower the pKa value, higher will be the acidic strength. Therefore, 2 greater than 1 greater than 4 greater than 3. So remember, once again, you don't have to memorize the values. Just to give a justification for the statements. Here I am giving you the value. I hope I made this concept clear to you, and if you still have any question, you can comment them in the comment section.